like and leave a heart, please.
There we go. Hello, everyone, and welcome to the show. This is the Vidor Locksmith Show, and I am so happy that you guys are here with us. Oh, another exciting Friday of great stuff. We finished out the Torque and Drag or the Learn It, Turn It, Burn It Torque and Drag mini-series this week. So thankful for everybody that tuned in and watched that over the last 8 weeks. And huge thanks to Brandon Foster, who helped me put that together. I know there's a lot of engineers out there around the world that are tuning in and watching that, getting a lot of thank yous and messages on LinkedIn from people that are watching that series. So really thankful for that. I will be putting together the rest of the presentations and putting those online over the next couple of days. So be on the lookout for that. Try to think of some other stuff. Just as normal, guys, let me know where you guys are watching from. I don't even know if I did the intro. This is the Vidor Locksmith Show, where we are unlocking the secrets to success in the oil and gas industry. One interview, one technical presentation, and one technical screw up at a time. Hopefully we'll find a quick technical screw up for today and get it out of the way and move on with the rest of the show. Been an absolutely amazing show, or absolutely amazing week. Witten presented this week at the Permian Basin Association of Directional Drilling. Was the keynote and moderator for the panel there. Huge thanks to all of the panelists from multiple different directional drilling companies that were there. Huge thanks for them for being there, and for everybody else that showed up and listened to me throughout the keynote. I had fun. Hopefully everybody else did too. So let's throw out some names there. So we've got Ian Burst watching from Woodlands, Texas. Thanks for being here, sir. John DeWart tuning in from Colorado. Thank you, sir. David Bradley tuning in from Pennsylvania. Barry Lacoste from Houston. And George tuning in from West Chase area in Houston. How are the numbers doing on there on LinkedIn?
Shows 16.
Okay. All right. I mean, we've got people watching, so all right, we'll get this going. Not as many people as per normal on a Friday, but hey, we'll keep it going. All right. So a couple of quick things I want to be able to share with you guys. Season 2 of How It's Done premieres this month. Season 2 of How It's Done premieres this month. Here's the intro for, I don't know, I can't remember if this is season 1's intro or season 2's intro, but regardless, this is the intro to the How It's Done show. Yeah, so that's the season 1 intro. We've already completed the season 2 intro. I just haven't uploaded it yet, but we will get that on there. I will be re-releasing all of season 1 How It's Done episodes over the next, I guess, 10 business days or so. What did we say we were going to premiere that? The 22nd. So, yeah. So we'll be re-releasing all of those throughout the month of March, leading up to the premiere. The first premiere will be March 22nd. I don't really know the time because I actually have a speaking engagement that day, so I might have to do it a little bit earlier in the morning. So maybe 10 a.m. or so. I can schedule those things on LinkedIn. So that's what we might do. So anyways, put your calendar, set that. Be on the lookout for season 2 of the How It's Done show. If you haven't seen any of those episodes, they're all on YouTube. Go over there and check them out. So John Dahl says Clyde's in the house. Frank tuning in from Louisiana. He's not up in Anchorage. All right. LinkedIn user from Spring, Texas. Thanks for being here. Doveran from Turkmenistan. Thanks for being here. And John tuning in from Anchorage. I'll be actually headed up to Anchorage at the end of this month. Next week, we're going to Norway. After that, Belgium, then Germany, back home for a week, then Alaska for a week. So a lot of running around. All right. As per normal, let's do the thing. If you guys would like to win a drill bit, put into the comment section right now. Hashtag PTEN for Patterson Energy. They are the new sponsor of the show. So very thankful for the sponsorship. Oh, so it's not just a drill bit. I almost forgot. We've also got this really cool, it's this ice cube thing. It's called rocks. But you can make custom little shaped ice cubes, little whiskey ice cubes, or I don't know, whatever you like to drink cold. Hot chocolate, whatever. All right. You'll get one of these, and as well, really nice Patterson hat. So hashtag P10 in the comment section right now. Please throw that out there, and we'll get you guys all loaded up to be in the running, or get you in the running to be able to get one of those. So while you guys are doing that, we play a quick little video from our sponsor.
Our newest alternative power technology is perhaps the most exciting, as Patterson-UTI expands the use of lithium-ion battery technology in our rig fleet. EcoCell is an energy management system that uses stored energy to decrease the number of generators needed online and keeps generators running in their most efficient power to emissions ratio range.
There we go. All right. So like this week is the week. If you want to win a drill bit, you better be putting that hashtag P10 in there. It's your odds are ever increasing this week versus weeks in the past. All right. So let me pull this one back off. Brand. Yeah, I'm getting all my buttons confused here. It's been a while since I've had to do it like this. Like, I don't know, 2 or 3 weeks. All right. And there we go. All right. So this week we've got 13. Hey, here's somebody's chance to be able to be a big winner. We'll give it 5, 4, 3, 2, 1. Draw. Okay. So just 13. So of the 13, who gets to be the lucky one to be able to win a drill bit and all the Patterson swag to go along with it? Barry Lacoste. Barry, send me a text, bro. I don't know. I've been to your house before. I just don't remember the address. But shoot me the address, and I'll get this stuff sent over to you. If I'm not, I'm not going to be in Houston anytime soon, so I won't be able to drop it off. But we'll get it mailed over to you, boss. Thanks for watching the show, Barry. All right, guys, let's get on with the show. We've got absolutely amazing guests here with us today. Let me make sure that I do this right before we go forward. Hold on. I gotta change because we're going to be doing some screen sharing, so a little bit of presenting here. All right. Share screen. Window. There we go. Share. All right. Whoa. Okay. I don't know if you guys saw this, all the movies. All right. So here we go. There we go. Thanks for being here, man.
Thanks for having me, man.
Appreciate it. So on the back of the Torque and Drag Miniseries, talking about all things torque and drag during drilling. And now you can talk to us about the torque and drag on the production side.
Yeah, so the story kind of came about, I guess, in the early days of your wanting to do the torque and drag series. I mean, I had this project that I've been working on for several years now, and I've been trying to get a patent on it. I actually did get the patent on it, but
congratulations.
At some point a few months ago, my examiner came back and said, "Hey, what you're doing here is basically a torque drag analysis that they do on drilling rigs," and sent me some pads. And I'm like, crap, now I got to argue, because I know nothing about drilling. Now I got to argue back to the patent examiner why it's not a torque drag analysis like they do on drilling rigs. So that's when I posted on LinkedIn about, hey, I kind of need to do a crash course in torque and drag analysis so that I can argue intelligently back to the patent office. And then you connected me with a bunch of folks, and I asked a bunch of dumb questions, and here I am now talking about what I was doing on the production side. So it's very similar to a torque drag analysis, but I'm coming at it from a completely different angle. So using analysis that we have been doing since the 60s on pumping units, basically applying that technology to a workover rig to measure drag, friction drag.
All right. So guys, if y'all have any questions regarding I'm looking at the wrong camera. Hold on, let me close that real quick. That'll help with the lighting situation. There we go. If you guys have got any questions regarding torque and drag on the production side, as Walter goes through the presentation, please put them in there. Be happy to be able to answer all their questions. I know that this is one of those things from the drilling side of the business. I know a lot of people have probably heard the conversation. It's like, oh, you got to make sure that, we can't put a big kinks in the top of the well because of sucker rod pumps and things like that. I've heard it dozens of times. I know plenty of other people have heard it dozens of times. Now let's actually hear it from somebody that's been on that side of the business and people that are having to deal with the problems that drilling creates, right? So if you've got questions or whatever, be sure to throw them out there. Love to be able to get everybody's thoughts and stuff. All right. So we still got people putting in the Patterson hashtag, but thanks guys, but we already did the drilling. So, all right. You want to start with your presentation? We go through that. All right.
Into that.
So what we'll do is we'll go ahead and put this up here on the screen, and then I'll switch spots with you, and then
drive over here.
Yeah, I think if we click here, then yep.
All right.
There you go.
All right. Yeah. So this is the drag analysis that I've been doing on production rigs. I've been posting a bunch of stuff on some cryptic stuff on LinkedIn with me and the dog out in the field. I haven't really gone through and discussed this in any public forum. I've done some papers on it in the past, but this is actually, I guess, my first broadcast discussion about it. So the first thing to describe here is it's not a torque analysis. I'm not actually turning the rods. I'm just doing a strict friction analysis using linear motion. So production, it's the thing that we do for the next 100 years. So this well, I took this picture in the background here. This is the Discovery well in Signal Hill, California. 2 years ago, I think. So it was sometime during the pandemic. It hit its 100th anniversary, and so all the stuff that I'm going to talk about today, all the dynamometer cards and all the rod analysis, that came in way after this, after this well was drilled. So we're constantly learning new things. This is proof of it. So I'll tell you, this well is still pumping. I just drove by it recently. They don't have the sign there anymore because it's not the 100th. It's the 101st or 102nd anniversary. But this well is still producing fluid. So when you drill a well, just remember it might be around for another 100 years.
I love that slide.
If you come out to California, I'll take you right by it. All right, so rod pump. It's the most common artificial lift method. I mean, it's everyone that thinks of the oil field thinks of the pump jack going up and down in West Texas there. The first thing that you need to kind of understand about rod pump is it doesn't actually suck the fluid out. So I've been in the industry for 20 something years now. When I first got in, I didn't realize it's a long steel rod that goes down to a pump at the bottom of the hole. Can I do a mouse over here? Does that work?
Yeah.
See that? Yeah. So you got this long, we call it a rod string that's attached to a downhole pump, and it's basically just two check valves. So the two check valves just alternate and lift the fluid. It basically pushes the fluid up from the bottom. You get thousands of barrels a day, all the way down to these stripper wells that barely produce anything. So it's a very wide range of production that you can get out of a rod pump. Again, the rod pulls up on the pump, and gravity pulls it down. It pushes the fluid to the surface. There's lots of shallow wells. There's lots of deep wells. The deepest one I ever worked on was 14,500 feet. So it's kind of all over the map. Obviously, the deeper you get, the less fluid you can produce because you're lifting all. Ooh, I'm flashing there. Is that cool? All right.
Yeah, it should be fun.
The more the deeper you are, the more you have to lift. So just horsepower constraints. But really, what we'll talk about here in a little bit is the diameter of the hole. That constrains a lot of stuff. So the size of the pump that you can fit downhole, the amount of fluid that you can actually produce from that well, and just some of the other, I don't know, I guess call it jewelry, some of the other like tubing configurations and equipment configurations that can all be constricted if you drill too narrow of a hole. And then the cool part about this is the rod, the sucker rod, the steel rod kind of acts. This is my animation, my janky animation of rod pump. It just acts as this really complicated long spring. So you're pulling up and down, or pulling up on the pump. The pumping unit's got a crank arm. It's accelerating, decelerating through the whole stroke. You got loads coming off and coming on at the same time, or at different times. Different spring constants because we do different size rods. It's a very complicated system. If there are any questions, feel free to stop.
Oh
me.
yeah. Well,
All right.
I'm just trying to soak all this in. So yeah, keep
All
going.
right. So I just put this slide in here just so you can kind of zoom in and see what the pump looks like. It's very, I mean, there's all kinds of variants of this, but it all comes down to the same concept of you have a standing valve that's kind of fixed, that's attached to the tubing, or it's fixed in the tubing. That valve just it's called the stationary valve or standing valve. It's stationary. When you lift up on the plunger, which is this guy right here, this is the moving part, the kind of the yellow, maybe orange color. That's the moving part. So when you stroke the well, you lift up on the plunger. That traveling valve carries the load, carries the fluid load, while the standing valve opens. That's this. We're lifting right here. This valve is closed. The traveling valve is closed, and fluid is entering the pump through the standing valve. So that's lifting fluid up, but it's also recharging the chamber of the pump. And then here we go to the downstroke. So the this guy, well, it's right at the start of the downstroke. So both valves are closed. This is actually the downstroke. So here the standing valve down here closes. So now no fluid can fall back out into the casing annulus, and all the fluid transfers from the pump chamber up above the traveling valve, so that when we come back around to the next stroke, the fluid can be lifted.
So there's a seal between. Point here. So there's a seal between the plunger and
it's a metal on metal seal. So it's just basically a really long, tight fit metal seal. It's a like a 3,000ths up to 15,000ths of an inch around. So it's really it's a metal on metal seal that does have some fluid leak past it, but that's partially for lubrication.
Yeah.
And it's really just something that doesn't wear out. If you put any kind of elastomer in there, any kind of like O-ring or anything like that, it would just get torn up. So, but just the metal on metal that works fine. It does have a little, we call it slippage. You can calculate that out, but really it's just to keep it lubricated.
Self-lubricating. I mean, there's oil.
Yeah. The pump chamber may not always be full. I'll talk a lot about the analysis that we can do. So when that pump chamber, if it sucks air in, or if there's gas in there, you can see that on a plot that we use, and that ties into the analysis that I'm going to talk about in depth. So, all right. So deviations. This is the crux of the issue here. So. When you have deviation, you know what I should have, can we switch back to the thing? I didn't really talk about the configuration. So you got the casing, you guys all know that from drilling, but then we have, here's my janky,
oh wait, no, we'll just go like this. There we go.
Ooh, all right. Whoa, is that coming through?
Yep.
All right. So before I left, I took a piece of, where's the camera? There it is. I'm backwards. All right. I took a piece of plexiglass tube and just got the air gun out and bent it and made a crooked wellbore. So in the rod pump world, we take tubing. So I'm going to use this white tube. So that's the production tubing. So we stick that into the wellbore. The pump's down here at the bottom of you can't even see it. Down here at the bottom. So all the fluid's going to go up through this inner tube, the production tubing. And then we have the sucker rod here that goes in through the production tubing, and it's just stroking up and down through the production tubing. So you can probably see that where you have this crook in the wellbore here, it's going to wear a hole in the production tubing, right? So the other thing, because that's disconcerting, the flashing, the friction that you see here. So if I drop this in here, it doesn't go down, right? Because it's being held up by this friction. So that's a problem. But really the problem is on the upstroke when you have the tension load on the rod string that's really cutting into the tubing. So I have pictures that, can you switch back to to the rod cut. So up here, I mean, you can see this is a piece of tubing that was, they cut it in half so you can see it, but there's a nice track worn in here, and it just blew out. hole in tubing blew out. We got to pull the whole well and replace that joint of tubing because there's a deviation there. Now, before I came here, I got some buddies that work at a pump shop in LA, and they gave me some pictures. These are the sucker rod. This guy right here. So this. Oh, I gotta go over here.
Yeah,
yeah.
Then they'll see it.
All right, there we go. Oh, there we go. All right. So this should be a round rod. So I mean, this is crazy. This is a square. This went in a round peg and a round hole, and it came out a square peg and a round hole because of the wear. This guy over here, this is worn on two sides. Well, the reason it's worn on different sides is because we do rotate the rods to even out the wear, but when it's so bad, the rods just kind of flop into their little track and wear on one side and then move over to another side and wear on that side and then move over.
Yeah.
And this kind of this cross section that I drew here, this is the production tubing, and this would be the rod. So this right down here, this is where it gets
pretty dicey,
pulled into the side because of the side load, because of the deviation, and that's the wear. This is the wear that you see here, and then this round rod. This should be a round rod, was worn on this side because of that side load. There's all kinds of other problems that come about from drilling. Especially, we don't really have this problem out in California as much, but definitely up in the Bakken, a lot of gassy wells. When you have these horizontals, they build up these gas slugs, and I'm not the right guy to talk about that, but when the gas builds up and it slugs up, that can cause all kinds of problem with the pump, because now it's supposed to be pumping fluid, but now all of a sudden it's just got this gas. So do we shut the pump down? Do we expect that gas is just going to clear out and we just keep pumping through it? There's all kinds of fun issues that we get to deal with because of these I'll call them undulations. I mean, it's just gas in the wellbore, but if the well doesn't have a good profile for producing that gas to get that up. Oh, and I'll talk about this later. Gas separation. So if you don't have a big enough area for that gas to separate out around the pump, it's got to go through the pump. So that's another problem there. Questions?
Oh, well, I should say this. We've got a comment that's already come in here from LinkedIn user. Thank you, LinkedIn user. Says, maybe a good reminder that drilling a crooked well fast to save money ends up costing everyone else down the line.
I love that. That should be my tagline right there. Thank you for throwing that out there. I do have a lot of questions about speed of drilling wells. So a lot of what I think is the problem is when they screw something up in the drilling and then they got to sidetrack out. I mean, I have a great story about some folks in I was in Oklahoma City, but they were from Colorado, and they were showing me pictures about this well. It would look kind of like this, but it was worse than this. And they're like, yeah, we got a week runtime on something like that. Looked something like that. Like, what the hell? What's going on? You know, what do your wellbore surveys look like? And they're like, well, we got the drilling surveys, but it's kind of missing that like 500-foot section where we're having all the trouble. So what happened? Well, the drilling guy screwed something up, and they just lost the survey for that. And so stuff like that. When we get these drilling surveys, the points of interest never have the data that we need on the drilling surveys. So we come back through, and I got some slides on that. We run gyro surveys through the tubing so that we can actually really get a better idea of what the wellbore looks like.
Wow. John DeWar says, Tyler Stops indeed shows the value of talking to production during the well design phase.
Yeah, I love it.
Yeah.
And if anyone wants to reach out, I mean, I know lots of folks that work in lots of companies on the production side. I can connect anyone up to talk more about this, because I mean, it's not just drilling. It's really I got a slide about Wall Street. It's, you know, people saying, hey, can we really get away with that 5.5-inch casing? It's so much cheaper than the you know, let's just cheap out on something. It's not necessarily drilling's fault. Somebody made a financial decision that is now negatively affecting the next 100 years. So keep that in mind. If you're drilling a well, somebody like me is going to have to deal with it 100 years from now, hopefully.
Wow. All right. Yeah. Let's
move along.
Yeah. Let's go to the next. There.
Can I get
Yeah.
back
Yeah,
on?
yeah, yeah, yeah.
All
yeah.
right.
Sure, you're good.
Yeah, so I talked a lot about this actually. If you think about it like compounding interest, I mean, every time you pull a well, so that well, maybe I shouldn't poke on that discovery well, but every time that well gets pulled, it costs some amount of money. So that builds up over time. So what you're saving right now and putting that narrow casing in, or not fixing that sidetrack right and getting it nice and straight in that area, that's just going to compound over the life of the well. So I don't have dollars in that. I reached out to a guy that did give me some dollars. When we have friction in a well, that also, remember we got this big spring pulling up and down on the pump. Some of that work is being wasted to friction. So it basically makes the effective travel of the pump less. So if you're stretching the spring every time instead of lifting the fluid every time, you're wasting some of that work that you're doing at surface to just stretching that spring because of that added drag. So he worked out, it was like, I think about 3 feet, I'm just going from memory, about 3 feet of every stroke was lost to just drag because he ran out of a straight well and with their deviation survey, and the drag load on that pump made the spring stretch that much more. So he came out to like, I don't know, 500, I should look it up, 500,000 or 5 million or something, like some five in there of lost production of just wasting that 3 foot of stroke every stroke. I mean, this is happening every day for 24/7 at probably 5 strokes a minute. When you work the numbers out, the cycle times on these are crazy. So let me get back to my slide here. So I talked about Wall Street. You know, it's not always drilling's fault. Somebody made a decision that they looked at a piece of paper and said, "Oh, we can save this, and well, we're going to sell that asset in 2 years anyway. So why would we even care about that?" I was talking to another guy from California, and I got some slides on that. But he was telling me about some software measure that, this is one of my dumb questions. He was telling me about a drilling difficulty index. It's a software value that comes out of some like, I don't know, Prosper or some software. And he was saying there's some sort of maybe correlation with if it's a hard well to drill. And I think he was more specifically saying if it's a hard well to drill because you're trying to reach a certain target or trying to stay within a certain zone, that might have a correlation to how bad it is or how hard it is to actually pump the well. So, I mean, if your wellbore's crooked, it's hard to drill, right? I mean, if your wellbore straight, you don't have to worry about your torque and drag analysis. If it's crooked, that's when you got to worry about it. So there's probably some discussions that could be had just on that. Like, hey, let's make it easier for everyone to.
I would say the thing that would probably match up would be there's not a definitive measurement for it, but for wellbore tortuosity. And I know several people there that have set up, Angus Jameson being one of them, who has tried to put together like essentially a figure or a number for how many deviations, turns, and changes in well path over the course of the well versus what it was planned to do. So there's a lot of that stuff
drilled in versus as planned. That's
yeah. So there's I don't know the drilling difficulty index. I haven't heard of that one.
If anyone knows anything
if anybody
about
that's
that,
watching that knows, if
I'm
that's
not hard
part
to get
of
a hold
like I don't know, maybe a software suite that's offered by Halliburton or something like that, I'm guessing that might be the case. But yeah, if anybody's watching it that has heard about that, can chime in, please let us know. But yeah, I mean, this is making me think, man, we need to get you and a couple of the other like wellbore surveying guys in the room at the same time and let y'all be able to talk it over.
Argue it out.
I mean, we're actually doing the industry steering committee for wellbore survey accuracy. Like we do 2 meetings a year, and then one of them's next week. So definitely kind of poke and prod them and say, hey, we should, the next one will probably be in San Antonio in October. We should probably have you come in and do another presentation and talk to everybody. So because this is great information. So yeah, I'll let you go ahead and.
Yeah. All right. So the size of the casing, I talked about that. Out in California, we do a lot of water floods, and they move a crazy amount of fluid. So I got some slide or a slide on some wells that were problematic, and they were relatively shallow wells, a couple thousand feet, but they were moving, I think he said, about 1,000 barrels a day and getting 200 barrels a day of oil out of that. So, I mean, that's a pretty, for a rod pump, that's a pretty substantial amount of fluid to be moving. To do that, you need to have a big tubing string, which means you have to have a casing that can fit that. Most of the rod wells are 2 7/8 tubing, except for these water flood ones that go 3.5, 4.5 inch production tubing. The narrow well bores restrict a lot. So I can't stress that enough. If you can put a big enough well bore in there, that might relieve some of the crookedness of the not all of us, but something to consider. Gas flows, I talked a little bit about that. I got a picture of a gas separator over here. So this is the pump right here that we normally deal with. It's really simple. Everything in this is really simple. So what we have is a dip tube. We call it a dip tube. That basically it's a tube that goes inside of another tube that's inside of the casing, and the fluid goes into that, and the fluid has to fall down so that it's basically like it's a straw in your soda glass. So it's trying to let all the bubbles go up, and you're drawing fluid in from the bottom, right?
Yeah.
If you don't have a big enough casing, you're restricted on the size of that separator. So the cross-sectional area is what makes the separators function. So you got to let the bubbles rise and let the fluid fall. But if you, and every half the time you're drawing fluid in, so the fluid's going down, the bubbles are coming up. If the fluid's going down faster than the bubbles are coming up, then you eventually overwhelm the separator and suck gas into the pump, which is less than ideal. You'd rather have the gas go up the casing because it just floats up and naturally comes out the casing.
Yeah.
If your casing's too small, then you don't have a lot of options in how big of a gas separator you can use. I threw this other one in here just because, I mean, if you look at some of my LinkedIn posts, I'm an armchair geothermal enthusiast. I've literally gone and knocked on doors and bended people's ears down in Southern California. There's a couple geothermal facilities down there. Some folks are talking about doing how would I say this? A geothermal battery. So basically using solar energy to heat up fluid, pump that down into the formation. In California, we do a lot of steam flood. So there's a lot of folks there that know how to heat up a reservoir. So the idea is you heat up the reservoir and then use that heat to run a turbine at night. It's brilliant if it proves out. I mean, people are proving that out. But if you have all these well bores out here, at some point they're going to be depleted, and if you have a well bore and this proves out, I mean that's a pretty cool second life of a well bore. Other stuff, I mean, the frac jobs, casing cement, that was just things that people threw out. If you have too narrow casing, then the amount of horsepower you need to frac that well goes up. So bigger well bores, straighter well bores. That's the takeaway from this question.
Yeah. So a great way to understand tortuosity impact on rods and pumps is the effective diameter. This identifies what can pass through a tortuous section without interference.
Yeah. So I got another thing on that. So it's not just rod pumps. So ESP, there's a whole world of other artificial lift methods. So there's progressing cavity pumps, rod pumps, ESPs, gas lift, plunger lift. There's all these different versions. I mean, I'm the rod pump guy, so that's what I'm here to talk about. But these tortuous wellbores, I mean, if you're trying to take a big ESP and you're trying to shove that through this bent tube here, I mean, if this was my ESP and I'm trying to put it through, or actually, I guess the ESP is on the production tubing, this doesn't go through, right? That's a problem. Or if it does go through, you got to push it through and bend it and potentially tweak the motor. So an ESP is just a electric motor with a bunch of they call them stages, impellers. So that's a big honking piece of equipment to shove through a bent hole. So if you bend it, then you could potentially damage a very expensive piece of equipment by trying to cram it through too tight of a hole, or too tortuous of a hole, I think.
And then Mark James says directional difficulty index, and then he put in a 1Petro link.
All right,
which can't click right now, but
I can get that later.
Yeah,
go read that.
We can grab. And then John DeWar says DDI has been around for years. It aggregates scores for various aspects of drilling a well. Directional drilling challenges is only part of it. There are various versions, but no industry standard. John DeWart's like the expert for us being here from the drilling side today.
I appreciate it. Maybe we need to get an industry standard that includes the life of the well.
Well, I know that there was at one point in time there was an attempt by a shell engineer, I cannot remember her name, that wanted to look at the correlation between drilling the well and the production, right? And like the straighter the wellbore, did that increase production? Well, maybe the thinking there is maybe it doesn't increase production, but it allows the production to happen without as many headaches.
Yeah.
And so maybe it's not like, oh, all of a sudden we go from being able to produce 1,000 barrels a day to 2,000 barrels a day. It's just we can keep doing 1,000 barrels a day without having to have the high maintenance cost of a BMW.
Yeah, every time you pull that well, it depends on the region, but it could be a $50,000 job to go in and replace all that tubing that was worn out. Not to mention all the downtime. It might take a month for you to get a rig out there. Depends on where you are. It depends on what the schedule is. It could be, there's wells that don't make that much that just are left down because we're always chasing the high, the high producers. So when they're down, you want to get those back online. So, the 10 barrel a day might be down for a month. When our 100 barrel a day goes down, you want to get the rig on that. So downtime is another big thing. Downtime and pulling costs. So if we can keep those down, save money, make more fluid. All right.
All right. Let's
Am I back on?
Yeah.
All right. Oh, here's the problematic well. That was the one from out in California. So I can't even talk about it. So this is where this came from. So production doesn't have a lot of tools, and we have some design, some I would call them basic design programs that let you model up the well in 3 dimensions and just kind of see what it's like. Really what they're trying to do is assess side loading. So my issue with those programs and anyone that draws a wellbore in 3 dimensions is they always want to squish the wellbore and make it fill up the screen. So we have 3 dimensions. You should have all 3 dimensions equal. If you have a very straight well, very straight well, and you squish it, it's going to exaggerate all of the deviations. So when you see a 3D well plot, look at the dimension, the X, Y, and Z, and see if they're all about equal. If the Z, the height of the well is 10,000 feet, and the X is like 50 feet, and you see this crooked wellbore, it might not be that crooked. So many years ago, I developed the 3dwellbore.com. It's a website that you can throw in deviation surveys, just upload them and just see them and kind of navigate around. So one guy wanted to overlay a bunch of wells. He was doing a talk to his drilling department, and I'm probably going to butcher it, but the wells that these were the shallow water flood wells. He was having all kinds of trouble with just this one kind of subset of wells. And he told me, I talked to him on the phone a bit about it, and he kind of described how they were drilled. It was like something about 9 degrees from the azimuth. I forgot what he was telling me about. I should have written it down. But anyway, his point was that he doesn't have a lot of trouble with where am I at? Over here. He doesn't have a lot of trouble with these. Relatively speaking, with these wells. But these guys, this cluster of wells here that was drilled like this for whatever reason, are a nightmare for him. So these are the kind of things that we should come together as an industry and say, hey, you're drilling a well like this. I mean, we got a lot of very, very simple rules of thumbs, like shallow deviations are worse than deep deviations. This is another kind of subset to consider. I probably will butcher it if I talk much more about that, but just talk to your drilling guys and see what wells they've had trouble with and which wells are good, and try to replicate the good wells. That would be the
I'm
takeaway.
guessing it might be them drilling east-west, if that's the case, because that's the 90-degree azimuth where your survey uncertainty can increase.
Wait, what?
If you're drilling east or west, because you're using magnetics to be able to drill there, so your magnetic interference can increase. So as far as your ellipse of uncertainty increases
In that direction, because is that because it's perpendicular to the field line?
Mhm.
Oh, okay. Huh. Well, that's what I learned today. All
There we
right.
go.
Cool. All right. Okay. So now, geez, we're 42 minutes in.
No, hey, we've got plenty of time.
So I got to talk a little bit about how we analyze rod pump wells, because that feeds into why I'm actually here and why I'm trying to talk about this drag analysis. So we use a thing called a dynamometer. It's very similar to what you'd use on a dyno on a gas engine. It's a measure of work that you do over the stroke. So what we do is we instrument the well. It's a load and position. The load is easy. We do a time sample load or weight. That's how many pounds you're lifting and what the position of that load is throughout the stroke. So we gather many samples through a stroke. We plot them against each other, and you get a plot like this guy up here. That for someone like me, I look at this and go, "Oh, I know exactly what's going on there." For some other folks here, it might be a little bit of a mystery. But
I can tell something's happening, but I can't tell you what's going on.
I'll show you that they simplified this position. I said that position's a little bit more of a challenge. There's some fun stuff that I'll talk about on this tool that I got. But basically, there's a bunch of different ways that you can get position. You can do it with an inclinometer. You can do it with they just have proc switches basically that are on the crank arm. So every time it goes around, it gives you a top stroke, and then you just kind of interpolate between those.
All right, real quick, we've got a question from Ian.
Yeah.
It says, how deep do the sucker rods typically go?
So I don't know if there's a typical well. I mean, it can go from hundreds of feet. I would say probably 1,000. I mean, you could have 100-foot wells. Usually probably about 1,000 foot down to maybe 15,000 is probably the deeper limit. Again, it's dependent on production rate. So, the 1,000-foot wells with the water flood that are making 1,500 barrels a day of fluid, producing fluid, you're not going to get that from a 15,000 foot well. It's just a matter of how much you're lifting. The upper end or the lower end, the deeper end is 15,000 feet. Okay. That's probably the easiest answer to that question.
All right, yeah, or you might have to click. Yeah, click there. There you go.
There we go.
You're
All
good
right.
to go.
So this is a wacky animation of the dyno is the load and the position, and we gather those over time, but then we plot them against each other. So this was my attempt to kind of show you where they're coming from. So I took a position plot, I just rotated it over and moved it over the side, and then just animated it. So this is the how you build a dynamometer card, by taking the load and plotting it against the position. And now it's screwy because the time goes away. But when you look at a dyno card, all those points were gathered over one stroke. So there's a time component in there. So when we talk about position, there's also velocity and acceleration. Oh, the Lego pump jack. I love it.
Yeah, there we go. So as you're
there we go. So real
oh yeah, mine's got a lot of torque built up into it. Oh, there it goes.
So real quick, when you look at this, you can see we're going on the upstroke right now. I'm just giving you the kind of play-by-play here. It's still on the upstroke because the position's increasing. We get here near the end. the pumping unit's kind of slowing down. We hit the top of stroke right about here, and then we're starting the downstroke. So now interesting things happen at the first part of the upstroke, the first part of the downstroke, middle of the stroke, the peak and minimum loads. Those are all things that people like me look at and go, oh, I know what's going on this well. The load we get with the load cell, strain gauges. Some companies do it with motor current. Position, like I said, it's a little bit harder. We can do it with an inclinometer, accelerometers on the polish rod, or just a simple magnet and pickup, or some crazy new things that I got cooked up here. I'll talk a little bit about at least one of them. And then here's just another view of the dynamometer. So I put this time-lapse picture up here. So this is kind of like a snapshot of one stroke. So you're kind of looking at the entirety of the stroke in one picture. So here we have, I'm talking about work or power. We have horsepower. So we have the 1 horsepower is 550 foot-pounds per second. So here we have the foot. Here's the foot dimension. We have the pound dimension here, applying those against each other. And then this whole time concept of, this happened over one stroke, or, it could be, I don't know, I should looked at how many strokes per minute this has. Let's say this was a 10-second stroke for going around. That amount of work has happened in that time. So we can actually take the area of this plot and give you a power, like how much power did it take. And then we also, I'll talk a little bit about this guy down here, this kind of rectangle thing. This is a calculated downhole card. So it's the same concept, but it's removing all of the stretchiness. So I'll talk about that in a couple slides here. So the surface dynamometer cards, the ones that I've been showing, most of the ones that I've been showing you here are these wobbly, complicated things that are hard for people to understand. I mean, when you've been looking at it enough, you kind of can look at a card and go, oh, yeah, it's going fast, it's going slow, but can you really tell what's going on? There's all these inertial dynamics. There's the crank arms accelerating, speeding up, slowing down. The rods are stretching. Sometimes they're moving. They're starting and stopping at different points in the wellbore if it's really deep. It's hard to look at these service cards and really see what's going on. So this is actually out of an API, one of the API specs. They did this in the 60s, and they used an analog computer to simulate this. I don't actually know what an analog computer looks like. I've got a degree in computer science, and I've never seen one. But the fun story about that is the guy, I'll talk a little bit about, Sam Gibbs. He was getting his math models going right around the same time, and they were going to use this to do all the design and simulation. And he comes in and says, "Well, I can just calculate this. It's just math. I can figure how to build these cards from math and not have this crazy." I think it was like it had springs, or it was the analog computer. I don't even know what that means. But it shows the work done stretching and accelerating the rods, work wasted to friction. But we really only want to have a snapshot of what's happening at the pump. So here's just just to orient ourselves. So surface card up here, surface card. We do some math, and then we get a downhole card. So this is that same plot that I showed over here. The blue plot is what we measure at surface, and then we feed it through this fun math equation, and we get the conditions at the pump, which are the conditions of the fluid column that's being lifted. So now there's some other things that happen in there. We don't really deal with friction so good in this model, but that's actually the point that I'm trying to get at here. In, I guess it would be the second half of this talk, which is going to be quite long. So in the 60s, this guy, Sam Gibbs, he comes out with this paper. I put the paper number up there. So anyone that knows SP papers, it goes to 1 Petro. I mean, 588. I mean, that's how long ago this was. I mean, there's 10,000s or something like that, 15,000s or whatever. So he figures out this math and simplifies it over the years. That's what we use. We call it the wave equation. They simplified it, so they started putting it on mouse pads. So I scanned a mouse pad here of the different. Now these are the downhole pump cards. These are the calculated downhole pump card shapes. So when you look at a card, it's supposed to be a nice rectangle. If it's got this like Oklahoma looking or shape, then you can say it's fluid pound. If it's kind of got like a little bit more of a swoop to it, there's gas interference. there's combinations of all these things that happen. I guess this is probably where I should stop and ask questions, because this is the part that
No, keep going. Keep going.
yeah, the simplification that the wave equation gave rod pump analysis. It made it so that we could look at a well and say, oh, this is what's happening. We need to pull this well, or oh no, it's doing this. So that was great in the 60s when we were doing 60s and 80s and whatnot, when we were drilling basically straight wells. But now that we have super gassy wells and crooked wells, it's not as easy as this. This is great for vertical wells, but not so much for deviated wells. And then I'll just put this other one in here. So rod part. So when the rods break and you're still stroking up and down on the well, you still see a load happen there. You still see a position. But when you calculate down to the pump, because there's no load being transferred on and off the pump, you have this basically what looks like a flat line. That's I put that. Remember this one, because when I talk about the analysis that I'm doing, when you're pulling a well, when you're working over a well, and you're pulling the rods out of the hole, it's basically this card is what you would calculate at the bottom of the rod string. So I'm going to try to use that to the wave equation, using this concept of the rod part to see where the friction's happening in the wellbore. That's the tagline of the next half of this talk.
Right. And John Dawson, or a couple of comments here. We've got, or probably somebody says probably about 30-degree inclination at the deepest. I'm not really sure. That was probably.
I mean, people run pumps way on the horizontal too. I mean, it's the pump itself will run anywhere.
And then Ian says, sounds like we need to run more RSS in the verticals. And then John Dahl says, mousepad is 1960s artificial intelligence. So, all right.
Yeah.
All right. Let's keep going.
All right, over here. All right, so we did a presentation. One of the things that I'm involved in is a downhole dynamometer project, where we're actually trying to measure these dyno cards downhole. They did a version of this in the 80s, where they built a tool that would go down in the rod string, and that would gather these dyno cards. And they did, unfortunately, they did. It proved the math worked, but they only did those on straight wells. So what we wanted to do is redo that project on deviated wells and see, because we don't really handle friction in the math as well as we should. We want to see, how we can improve our models. But so this, I stole these 3 slides from that presentation. So this is a relatively vertical wellbore, nice, kind of straight, kind of maybe veers off a little bit. Oh, this is actually what I was talking about, the dimensions. So we go from 0 to 7,600 here, but we go from 0 to what is that? 1,400. So we're like 4 times taller than we are wide here. If I did the math, I don't think I did the math right there, but this is squished. So this is exaggerated. This isn't as bad as it looks. But when I look at this card, I go, okay, well, first of all, I can see that this well's probably running relatively slow, but it also has some unique shapes here. So go to the mouse pad, look it up, and we can see maybe a little bit of tubing movement. It's got this little kind of slant to it, but really we see this this signature right here. That's fluid pound. So we can analyze this well. We can say, okay, that's what's happening. So on our controllers that control the well, we can change the set point, so it might slow it down, or it might stop the well. If we have a VFD on it, we might slow the well down so that it matches the inflow to the pumping rate. But when we start getting deviations, so here we have a deep deviation, and
there we go.
Okay. Here we have a deep deviation, and now it's a little bit wonkier. It's kind of rounded over here. It's kind of rounded here a little bit. Could we say maybe tubing movement? Let's look at our cheat sheet here. So what's going on? Do we got
it's not the top left one. I can say that as well.
It's definitely not a flow. I mean, it's probably a full pump, but what is it? Can we really tell that? Can we tell if something's going wrong here? It's probably not the pump hitting down. We'd see like a tag, what we call a tag, a little load increase. It's probably not a bent pump barrel. I mean, you look at this, and if you didn't realize that this was a deviated well, you would say, hey, this bump right here might be a bent a pump issue, but it's not really. This is probably more of a fluid acceleration. The worn worn plunger or traveling valve, this rounded over. I mean, you might look at that and say that's what's going on, but I wouldn't be confident in that. And fluid friction, fluid friction's happening there. It's probably drag friction, but like where in the well is that? How bad is it? Is it, what is that obscuring as far as further analysis? And now here we have a shallow deviation. These are the really tricky ones because not only do you're pulling the load's increasing, which is increasing the side load, which is then increasing the tension load. So that screws everything up. So now you got this downhole pump card that you'd hope would be a nice rectangle, but now it's like this weird stretched out, twisted up thing. So you look at this and you go, I can't tell what's going on in that well. Well, what's going? I mean, we're just going to run it until something breaks. I mean, that's not
just going to run it until it breaks.
I mean, that's unfortunately that's how most of these rod pumps end up. And so here's just another shot of this. So we have the computed cards and the actual cards. This project that I was talking about, we're actually building a tool to go downhole to measure these cards in the well in deviation, so we can better adjust our models so we can include friction. That's probably, if you have any questions on that, give me a shout.
Yeah.
I did this. I put this SB paper. I wrote this a while ago. So some of the 3D wellbore stuff that I did, I realized, hey, I can use that same kind of plotting that I developed for that, and I could plot what's going on in between the surface and pump. So I just threw these in there because they're colorful plots. But basically, what this guy down here shows, I'm showing you each of these lines right here. So that's at a distance along the rod string. So I'm recalculating the car. I'm redoing the calculations at each step. It's a finite element analysis.
Wow.
So there's a lot of cool stuff that you could do on this because you're taking this. Remember, you have load as one dimension, you have position as another dimension, position through the stroke as another dimension, but you also have position as depth from the stroke. But then you have this whole time component that's in there. So there's all kinds of fun stuff that this is a whole nother topic that I could talk for hours on. But basically, it's a finite element analysis. And that's actually the one of the methods that we use to calculate the cards. It's finite differences is the mathematical term. And I kind of suck at math, so that's about as comfortable as I am talking about that in public.
Looks like you're a lot more comfortable with math than I am. So.
Oh, no, I'm just persistent. I mean, I worked through all of this, but it took me a long time. All right, so I could play those videos, but we're probably running out of time. I posted them a while back.
There's no time constraints.
Yeah, well, I haven't even got to the fun stuff, man.
All right.
So
we do have LinkedIn user who says, very informative. Thank you. I think this is a lot of new information for everybody on the drilling side. So there's definitely a lot to be.
Yeah, sorry if I'm going fast. I usually tend to be quiet 90% of the time, but when I start talking, I can't shut up. So, and I also steal a lot of presentations that I've done in the past. So I put this one in here because it's fun and it shows deviations and not just deviations from drilling, but this was oh geez. Okay, so when we put this tubing in the wellbore, we'll also put an anchor in it, and we'll stretch the tubing so that the tubing. It's kind of weird when you pump tubing that's loose in the wellbore. It kind of acts like an accordion. It kind of like shrinks and grows and shrinks and grows. And the problem with that is all that slack goes to the bottom, and then the tubing being slacked up at the bottom kind of corkscrews around, and then that creates side loads that impact the rods, that wear out the rods. So if we pull tension in the tubing by anchoring it, we can stretch out the tubing and keep that nice and straight so the tubing doesn't deflect into the rods. So this came about with a guy up in Montana. Wish I could name names, but I don't know if I can. He was having issues because they were putting a lower grade of tubing in. It was a hot well, and so they were worried about pulling the amount of tension that they needed to pull to overcome the temperature elongation and all the other stuff was going to overload the tubing. So they were like, well, we can't pull that much tension in this tubing with this grade of tubing that we have in here. And he was like, well, I mean, we were getting all these deep rod cuts on tubing, deep holes in tubing, because that slack is ending up at the bottom. So he goes out and convinces somebody to run a through tubing gyro. So they came up on the well that went down. They ran a through tubing gyro, and then they pulled some more tension in it, and they ran another through tubing gyro. So now you have two gyros that should match up perfectly, right? So he had this data, and I'm like, oh man, that's perfect. Give me that data. I gotta see what I can model up, because I got this modeling tool, and I'm sitting there thinking, well, how am I going to compare these two deviation surveys to quantify how different they are? So, well, I can do a visualization on it. So what I'm showing here, so it was a relatively straight wellbore. What I'm showing is I'm recalculating all these. Let me go here. So this is the whole wellbore on the left side of the screen here. So the green is one wellbore going all the way straight down. And what I did was I took every 25 feet, I took the survey from the other wellbore, and I started at that same point and ran it out for 25 feet. And then that vector that I got from the difference between the first survey and the second survey over that 25-foot interval, I just drew a line. So each of these little spikes, each of these little lines, that's just saying that the survey changed from one survey to the other by this much in this direction. Right?
Okay.
There's a lot to take in there. So the theory here is, if the survey is the same, those arrows shouldn't be. You shouldn't have any arrows. They should be the same.
Yeah.
But they're not. So there's
but they're not. It's the oil field.
there's variance in there. So I guess the other thing I didn't put on this one is, I think when I ran out the two surveys over the whole depth of the well, they were off by like 5 or 6 feet, which, I mean, I think that's pretty good over, I don't know, this might have been a 10,000 foot well. I think that's pretty good, but I mean, it's not perfect. So 5 feet, I mean, it's clearly outside of the casing. But so I'm just trying to quantify, I'm trying to bound the error. So when we do the calculations on the azimuth inclination, measure depth, azimuth, and inclination, those errors compound over the length of the wellbore.
Yes.
So I was trying to bound that by saying, okay, well, every 25 feet, and I did this every foot. It was 1 foot survey samples. So every foot I calculated 25 feet, and then that was the difference. And then the next foot, another 25 feet. That's where I drew all these lines. But what I got down at the bottom, so if you look over on the left here, something, it's the arrows are mostly in one direction here, then they kind of switch over, and they're mostly in the other direction for the big chunk of the wellbore, all the way down here. And then when you get down to the bottom, all of a sudden they start kind of going all which way. And this is zoomed in on the bottom here. So I don't have any proof of this, but this sure fits my theory of, if there was slack in that original, when they first came up to that well, when the tubing wasn't under as much tension, all that slack ended up, gravity pulled that slack down to the bottom. So one of those surveys at the bottom is tortuous, or it's not as straight as the second survey, because when they did the second survey, they pulled all that slack out of the tubing, which pulled the slack up from the bottom. So that's a long recap of this other talk that I did.
Man, I've got to get you in touch with some of these the survey guys, because the stuff that you're talking about is very, very interesting, and I'm loving this conversation. So don't let me stop it. Keep going.
Well, I don't know if I think that was it. There we go. Yeah. So I threw this in it was, I think it was part of that talk. My last dog, when I was doing this, she blew out her knee. I was prepping the slides. This is 6, 7 years ago. Prepping the slides, and the vet. I feel bad telling the story now. I mean, I told it then when she was alive. I'm like, that I need that picture because I'm doing a talk on dog leg severity, and this is perfect.
It's
So,
literally the dogs.
yeah, so they there's a whole thing. I mean, the golden retrievers, they blow out their knees. We got another one, so great dogs. But yeah, so we got the very expensive X-ray so that I could milk that X-ray for now probably 3 or 4 different presentations. So the point of this slide though is we always like these rules of thumb. So folks always say, hey, you know, keep it under 3 degrees for your dog legs in your wellbores and you'll be fine. It's probably a good rule of thumb. I mean, if you're going over that, there's probably a problem, but I would say it's probably not the best rule of thumb. I mean, straighter the better. The deeper you are, the more you can deviate. If you're shallow, don't deviate at all. Also, the degrees per 100 feet, that's a terrible measure. I've had people ask me all the time, you know, like, hey, I got these gyro surveys and it's running out to 90 degrees per 100 feet. Well, because there's confusion on how you scale. If you have a 1 foot survey and it changes a lot in 1 foot, do you just multiply that out by 100 feet and that's what your dog leg is or DLS for 100 feet? There's a lot of confusion in that world. In our world.
Yeah. There's a lot of debates on that.
Yeah.
And I don't want to jump into that one right now, but yeah, there's a lot of debates there.
So I'm just throwing that out as there's could be better ways to identify this. Really, I mean, it's a way to identify the worst spots with respect to the geometry and where you're kind of going, but maybe they're not great for like, hey, my buddies up there in Colorado, hey, we had this well and we just missed this 50-foot section where they did something really screwy, and that's just gone. When you take a survey of before and after, it looks fine. During that 100 feet, you can change all kinds of stuff. So shallow deviations are worse in general, but deviations distort the card more, or may distort the card more. That's up for debate. Anyway, all right. So this is the guy that I talked about. He's the guy that invented the math. I was fortunate enough to meet him. He had this thing called the Gibbs conjecture. This is probably the craziest theory thing that I'm going to throw out at you. Because we don't adequately deal with friction in our calculations when we're doing these wave equations or this wave equation math, at least on the measured side. So there's a whole nother parallel side where we take theoretical loads and positions, but at the surface and at the pump, and we try to figure out what the pump should be doing. There's 2 different approaches to this. So there's the diagnostic approach that I've been talking about, but then there's also the predictive approach where you try to figure out like, hey, I have this well and I want to put a rod pump in it. What's the pump card going to look like? You can run out the theoreticals that way. And there's some software programs out there that do include friction in that and do deviated wellbores, but the results are kind of iffy at best. So the reason for that is the Gibbs conjecture. He says basically any error, if you don't account for friction, it's just going to end up in the pump card, right? So it's pretty simple, pretty basic. I have an analogy here that my buddy Lynn Rowland said. The pump card is the trash can where all the friction ends up. So when we and those slides that I had with the distorted pump card, I mean that's what I'm showing here. That's you could call it now a trash can because it doesn't look great. But what I want to do, what I'm going to talk about here shortly is use that to my advantage. So when you're pulling the well, when you have a workover rig and you're pulling each stick of rods out, if you calculate that trash can over that length of rod that's in the hole, well, now you have a measure of the cumulative friction acting on the length of rods that are in the hole. And then you have a shorter length of rods and then a shorter length of rods. And if you calculate that for each of those length of rods, maybe you can map the friction of the wellbore. That's the theory. And that's the tool that I've developed, and I have not had a ton of time to analyze the data. But here's just another shot of some of the wonky cards that you can get. You can get these, we call them rhino horns, this green guy in the background here, where you get this. This one right here. The red is the predicted card. That's what the wave equation tells us that well should look like. And then the blue is a measured card from the same well using measured surface data. And this friction here is weird. It's just it's affecting at the end of the stroke because it's slowing down there, and so that friction's now transitioned from dynamic sliding friction to static friction. So there's all kinds of fun stuff to be had here. So the key points. So remember I said look at that flowing parted well. That's the same kind of card that we're dealing with when we're pulling a well with a workover rig, but we don't have a way to measure that on a workover rig. So I'm trying to use that friction, the Gibbs conjecture, with the friction ending up in just a cumulative value over what's in the hole, and trying to narrow that down as you're shortening that length. The deviation survey has got a bunch of points, contact points, but I mean it's kind of screwy how we do the deviation surveys, because we take these vectors and then we convert them into 3D XYZ coordinates, but then we actually really want a vector of the normal force that's acting on and gravity, and so we take this abstract measurement of these two directions, the azimuth and inclination, at a point, and then we convert it to something, and then we convert it to something else. So it's very far from what's actually happening. So I actually want to see, can I measure what's actually happening in this in the rod string, as opposed to what is the geometry of it, and then try to figure out what should be happening. All right, questions?
No, I'm nothing from me and nothing from the audience. Guys, if y'all do have any questions, feel free to throw them out there. But I'm learning a lot today.
So I got a picture. So this is the remember I said it was Sam Gibbs. This is one of the controllers that he developed. His name. Oh, sorry, I'm on the wrong screen. His name's Sam, so they called it the Sam controller. They've since renamed it. But he would always say, I wish I knew the numbers, but he's like, yeah, we got so many of these controllers out in the world, so many thousands of these controllers, and it's running it, let's say 6 times a set or 6 times a minute. He would tell you how many times a day his wave equation was solving the because of all these controllers that were out there. So it's kind of fun. He was a great guy, super smart guy, super nice. He was the kind of guy that would tell you you're an idiot, but in the nicest way possible. You know, like just I'd ask him questions. He'd go and pull his book off his shelf, and then he'd just read a page out of his book. I'm like, yeah, I read that, but it's easier for me to ask a dumb question than it is for me to go look in a book. So anyway, I said the workover rig generates the data. So can we measure it? So this is my time machine. So way back in 2019, I started doing some other projects, sensor projects, and I was like, hey, it's a load cell. I mean, I could just stick some sensors on something to measure what's going on the workover rig. So nothing exists. So maybe I could just build one. So it was back in 2019. I actually looked up, the first time I talked to you was January 2020, and the world shut down after like a month later. So
yeah.
This project has gone through some very interesting quirks over the years. So we talk a little bit about workover rig technology. It's not a drilling rig. I mean, they can do some. I mean, they use the same terminology in a lot of it, but you get the hydraulic load indicator that works off the deflection of the cable. Sometimes, especially when they're running rods, what they'll do is they'll double up the drum, so both cables are running, so they can go extra fast. So then you don't even get load. You just there's no load indication, so it's just up to the tool pusher to know if he's overloaded. Which I mean, it's pretty obvious. I mean, you're dealing with less than 50,000 pounds of load. So if your rig's bogging down, you'll know. But if something, it's not enough to, even if you have a load indicator like that, you don't have enough fidelity in that measurement to tell you whether it's friction or just noise. They also have this other guy here. This is for the sand line. It's a wheel with a little one of those counting wheels. It's every time it goes around, it clicks a number.
Yeah.
So that's what they use on the sand line to measure position. I mean, really, you don't need to measure position on a workover rig because you're just counting joints of pipe or joints of sticks of rod going in. So nothing exists on that. So I ended up having to develop one of my own, and that's down there. Is this a good time to show that?
Oh yeah, yeah.
It's heavy. You want to flip the camera? Or?
Oh yeah. Here, let's that.
So this is version 2 with less crushable plastic. Basically, this just shackles in. I got a picture of that, just so you can see how big it is. You shackle that into the rod hook. Should I tell the story about the dog? Oh, actually, that's the next slide. I'll tell the story about it. So I've had so many like just stupid roadblocks on this project. So I got it working. I've basically been asking for people to do like, hey, I got this wacky thing I want to run on your workover rig. Can you run it? You know, I fortunately have a lot of good connections out there in California. So people like one guy, Rennick, he's great. He's like always up for listening to me talk about my wacky theories. And he was running his own field. He had his own workover rig, and I kept bugging him. Hey, can I run it? Yeah, okay, go for it. The first one, I got a picture of it. I'll show that, where I just took the first version of it, wrapped it up in a bag, and stuck it on the blocks because I just wanted to see some data. Then when I finally got it running, they got stuck on an abandonment for like 2 months. And so I was like, I'd come by like, hey, how's the abandonment? Oh no, we're still stuck on it. So and then then I got the opportunity to run it. One of the I get up there, I'm all excited. I go to put it together because I have a little SD card where the data's logging, and I had the 3D printed housing, but I put it on backwards and I was screwing the screws down and snapped the SD card off. Like, so I had to go over to the guys that I've been bugging for months. Like, hey guys, thank you for telling me that you're going to pull this well, but I just broke it. So you waited for me for nothing.
Oh,
And then COVID hit, and then just nothing but trouble. So anyway, COVID goes, and that was basically what's in this picture. I had that ready to go, and then the world shut down. And then just the stars never got into alignment until so get back to that. It's prototype logging the high frequency data that I need to run through the wave equation to do this process, or to process this for getting rid of the dynamic effects. It's a battery powered device, which is really what's the scary part about it, because I was personally worried about somebody whacking with a pipe wrench, but turns out when it's on the rig, it's actually safer because it's above anyone's head. So unless the guy in the derrick whacks it on its way up, nobody can actually touch it. It's safer on the rig than it is on the ground. But it's still a battery powered device. I'm working on a shield and stuff for it. But I do have a live feed, so you can see basically you can see a rough position and the load. So there's some utility in that just for the rig crew. But it's really logging the high frequency data so that I can post process it. Here we go. This is what it looks like on the rig. So it needs this is this guy right here. So it needs a second shackle. This is the rod hook. This is what actually they use to lift the rods. These are the bales that go up to the blocks, to the cable, and lift it up. Usually what they do is they just shackle the rod hook straight to this. So I'm just going in line there. So I'm reading the direct load off of the rod hook and the position at that point. Which load and position, I didn't talk enough about it, but those need to be synchronized in time, but also at the same place for you to run the math out. Once it's installed, I mean, it's just don't whack it with a pipe wrench. I mean, that's the biggest. I should have brought the other one, but it actually had a battle scar on it because I got the 3D printed stuff. So there's just like a little nick out of it. I'm like, oh, it's finally something nothing bad happened, but it actually got whacked with something. And then if they're going to overload it, if something gets stuck downhole, just pull it out just for safety. And then here's the general process, and I've oversimplified a lot of this. Basically, so you got the blocks. Here's the rod hook, and then here's a stick of rod. So they have these things called rod elevators. There's two of them. They alternate out. So one's on the rod table holding the rods, while the other one's on the hook going up to get the next one. So here on
Show right now.
here on the A,
Here, open it up.
we're on the plot. We have the load is the kind of red yellow line, and then the position is the black line. So basically, the idea is I'm gathering the load and position. I'm just plotting them separate on the same plot, but I'm plotting them separately, so you can see the blocks are high here at point A. Oh no, so, there we go. Are high here at point A. The blocks are high, the load's low because we don't have any load. We're not lifting the rods. Then we go to B here. We take the rods, we stick them on here, we thread them in. We're going in the hole, but we thread the rods on, and then we lift somewhere between A and or B and C here. So the load comes up. So we pick up the load, where the blocks are still high. We pick up the load, so we see the load go up. And then that lets you pull the rod elevator out of the rod table. So now you can take this whole assembly and lower it into the wellbore. But while you're lowering it this is during D right here. So between C and E, you have this load as the rods are going in the hole. So the position is going down, right? But you can see that even the position kind of goes down smoothly. The load's bouncing all over the place. So there's accelerations happening in the even though it looks relatively smooth on the load, there's accelerations happening there, and there's the load fluctuations. So the part that I didn't do or haven't been able to do yet, because I've been sorting through the data, and this isn't even really a full-time project, is take this data and calculate the downhole card. So the whole thing with this torque drag analysis, I wanted to get in while it was still fresh. So maybe a little bit premature, but the data that I'm seeing is phenomenal in here. So basically this is one stroke. So you can see the blocks go back up, but they're unloaded. So that's for the next stick of rods. Do we have any questions?
Nope.
That's a lot to take in. That was going in the hole, so the same process goes in reverse coming out roughly, where you're just alternating the rod elevator onto the hook, and then you're lifting the rods and then setting them aside. It's basically the same. I talked a little bit about this. What could go wrong? I filled out 2 full slides on all the stupid things that happen. I got a great story from the last one. I'm going to get to that because it's hilarious. It's still a prototype. Basically, when I get a rig crew, I buy them lunch. So at some point, hopefully, I'll flip that to actually, instead of spending money to run this, somebody will pay me to run it. But right now, I'm just I've had to fix a bunch of stuff on it where I was gathering the data. I had some timing issues. I had some sensor issues. I mean, it's a prototype, so I was working through all that. I'm pretty close on that now. I have a data set that I think I can run through the wave equation. I just got that before I got on my road trip out here. Turns out it's safer on the rig. All right, so first time I ran it. So this is the story about the dog. So we were going, the wife and I were going to Galveston. It was the big SPE artificial lift conference. And I get the call, hey, oh no, it was Black Gold the week before. The folks that I work with at Black Gold, the pump shop that gave me those pictures of the square rod and the round hole. He's got a well in his yard that he always does fun experiments on. So I come up there one day and they're pulling the well. I go, Mike, what's going on? You're pulling your well. I've been, he's like, it's a new rig crew. I'm like, oh, okay, I get it. But I mean, it's a missed opportunity. But Rennick's pulling a well tomorrow just down the street. So I call Rennick up and he's like, oh yeah, they'll be I think they were running rods in. They'll be running rods in at, I don't know, 10 o'clock. And I'm like, perfect. I got to drop the dog off at my mom's house because we're getting on a plane the next day to go out to Galveston. I'm doing we did like a Houston thing, vacation / working thing. So I got to drop the dog off at my mom's house, who lives kind of in that area. So I'm like, oh, perfect. Okay, so 10 o'clock. All right, I'll drop the dog off at my mom's. I'll have plenty of time. I'm driving up. About 9 o'clock, I get a call from Renegade. He's like, hey, are you there? I'm like, no, you said 10 o'clock. It's like, oh, they started early. Like, when does a crew ever start early, right? It's always later. So it's like, yeah, if you don't get there right now, you're going to miss it. So I'm like, well, I guess, dog, you're coming with me to the field. So I take her out there, and I'm like, well, I mean, she must be my good luck charm, because I've been literally trying to do this for 4 years at that point. And finally I get out there with the dog, and everything goes smoothly. I get data. I'm like, this is perfect. So now she's my mascot. So now I got to take her every time I go because I'm worried if I don't take her, something's going to go wrong. So anyway, so that was the first run. Had lots of stuff to fix, but it proved out it worked. Like I saw it. Now I can say, hey, somebody who wants to run the first experimental tool, right? Now it's been out there, so you can say, hey, it actually worked. Here's what you can see from it. So then I get another one. The day before. Okay, so the day before this picture, I go to another location with it, and I'm like, hey, can I run it? It's like, yeah, cool. Go. They're pulling well right now. So I go over to the crew, and I didn't have a second shackle, so I couldn't run it. But he's like, oh, but we're pulling this well tomorrow. I'm like, I got to go get the dog. Now I'm going to bring the dog back. And of course, with the dog there, everything went perfect. I did post this video. It's the whole process of the load and position. If you want to watch that, I don't know. Do we care about that? Can we do this?
Sure. Click and see what happens.
I'll let you.
So. Is it gonna? Oh no, it's not gonna. Hold on, guys. Move. Present. Share screen. Let's do entire screen. Let's do that one. Share. And the stream. Oops. Put it on that one. There we go. Oh, there it goes. Or is it? Yep, there.
Yeah, just pause it there. All right. So this is that same plot. No, keep going. So this is that same plot that I showed earlier. It's just the block height is the black line. The red is the hook load. So pause it here. So they raised the hook. I cut the audio out, but it's pickle brick. I'll use pickle. So there's a thing that they use to hold the rods. It's called the pickle. That's a little bit of stupid inside joke deal. So anyway, so you can see each of these things is a stroke of the rig when the load goes up. So something wacky happened there. I'm not sure exactly what. I mean, I remember there was some yelling and something happened. Here the load dropped off, but then they picked it up again, and then they picked it up again right there, and then they finally dropped it off. So figuring out what was the stroke and what joint of equipment went in or came out is a little bit of a challenge, because like there's not a lot of there's a lot of consistency. I mean, there's one right there in the middle. That's weird. They dropped it down. Here's another one. They picked up the load. They waited. I don't know what they were doing there. Here they held the load at the top. So you can see all these things. Most of the strokes are consistent. They held some load there. Maybe they probably took lunch there. They just put some tension on it to keep it from flopping in the wind. And then here's like towards the end of it where they were pulling the K-bars out and probably the pump at some point here. And so the idea is to take all of this data now, split those into individual strokes, and I got some snapshots of that. There's again the picture of the dyno. And we can switch back. That's pretty much that. Oh, there we go. All right, we're back. So I had some temperature and timing issues that I had to work out. accelerometer issues. Oh, I didn't talk about how I'm getting position. This is the cool new exciting thing. Part of the position, so the black line that I've been showing here, that's entirely barometric pressure. So just like what they use with airplanes, just the height of the pressure, the air pressure of the tool. So when you lift that up, it's less pressure than it is down there. So that's what I'm using for one measure of position. It turns out it's pretty good for like, are you high or low? Is the blocks, are they high or are they low? You can get like to 6 inches of that. There was some issues with that. If you watch that video again, knowing that, and you watch that black line, you'll see it move over time. So air pressure changes over time. So I got another piece to this. Actually, oh yeah, here it is. So I took another piece on another device that had a barometric pressure sensor on it that was stationary, that would talk to the device that's moving up and down and tell the and have a correction of this is what the barometric pressure is at a stationary point. So you could take this. So this blue here is the position of this run over time, and you can see the pressure drift. So the air pressure drift. But when you compensate that with the stationary pressure, you just subtract the two, and now they're relatively equal. So that's not anywhere near good enough for what I need in terms of position. It's good for 6 inches, but it's not good enough to do what I need to do. So I have this accelerometer on there that you can correlate the two. I didn't talk a lot about the load pickup and drop off. So there's a lot of processing that I am in the midst of doing. And if I wasn't on this road trip last week and next week, I would be doing that right now. But taking the accelerometer data and fixing that, because accelerometer data has its own issues. The barometric pressure has its issues. Accelerometer has its issues. There's this load transfer that I can kind of synchronize to get a distance from one point to the other. But fusing all those up is the fun
challenge.
part. Yeah, I'll call it a fun part. But yeah, it's definitely a challenge, especially when you're dealing with what I was dealing with, just like bad data that I screwed this up. Oh, I had a temperature issue. Oh, this. So anyway, that was, I think, the third run. This one, I just to show, I didn't actually have a picture. I had a picture of it without the load cell in there, but just to give you an idea. So on the blocks, you got this swivel spring. So right here, it's just a big giant spring that just kind of soaks up some load. And then there's a smaller spring down here on the rod hook. So when you look at the data, you can see, hey, this is when they drop the load off. You can see this the impact load of that echoing through the spring as it's compressing. So like, I don't know, I threw that in there because I thought it was pretty cool. I need to get a picture of the spring extended with the load cell in there, but that's basically what it's showing, is that the compression of that spring when you zoom in.
Yeah.
This was 2 weeks ago, just before I left, and this is where I'm going to tell the fun story. So if you're watching the news, you know that California has had a bunch of crazy weather lately that we normally never have. So I get you get the call, buddy Rennick, hey, we're pulling a well, because some of these I was doing it on the way in. I think it's better data coming on the way out, because it's under tension load. When you're going in to measure friction, it's like if the friction's working against it, you just reduce that amount of load by whatever it's being held up. If you're pulling it out, that's additive load. So I think that you'd get better data from pulling than from running in, but you could do it on both. So anyway, so I wanted to get now that I've fixed a bunch of stuff, I wanted to get data from a well that they were pulling. So I get this call, like, hey, dog, come on, you're coming with me. Hop in the car, get up there. I'm checking the weather because the weather's coming in, the rain's coming in. I'm like, well, I mean, it says it's going to start at 10 a.m. and I'm going to get in there at 8. This is a shallow well, so they probably have it out in 2 hours. I'm like, I may be able to get in and out before the rain. This is awesome, because that's not waterproof. It got rained on a little bit, but didn't short out. So pull the well, get everything. I get on the tailgate. Because I have the SD card in there. In the first version, I had to take it apart to unplug the battery. So I'm on the tailgate, and it's raining. It's like the rain is on me, but I see the rain, like the real rain's coming, and it's like right there. It's across the street. So I'm like tearing it apart, get the SD card out, put it on the tailgate, put the cap back on, put it in, throw it in the back of my truck, flip the tailgate up, and I'm off and going. I'm like, guys, thanks. Sucks that you're pulling the tubing now in the rain, but at least I got out of here. So I drive around the rest of the day, make a couple other stops, do another project, some more sensing, and then I go, oh crap, I left the SD. I don't remember taking. Normally, I would take the SD card out, download it on my computer, but because the rain was coming, I was all flustered with trying to get in while it's raining on me before the real rain gets there. Flip the tailgate up. I have no idea where the SD card is. So I pull over the side of the road. It's like right at the edge, like, you know, that little crack in the tailgate. It's like about ready to fall out. I just got it because it was wet. The SD card was in water. It was kind of like stuck to the.
Oh.
So I'm like, oh, this is perfect. Oh man, I just saved the day. So I take the SD card out. I stick it in my center console, and this is the fun part. So the shift knob. I put stuff in the little thing where the shifter is, and it would always be thicker than an SD card. I never even thought about it, but it's just like a little conveyor belt that sucks into this little zone, right? So I'm like, okay, I'm at another well. I'm doing another project, so I'm literally sitting at a well for like 3 hours later that day. I'm like, whoa, I mean, I can just I could take the center console apart. So I find it. So it's right here, right? That's the SD card. So I'm watching YouTube videos. How do you take apart a center console on an F-150? It's all like snapped together kind of stuff. So pretty easy. So I get this stupid card. So I lost it once on the tailgate. I lost it the second time through my own fault, into the little conveyor belt that sucks it into this area. So I'm there with trying to pick it out with my fingers, and I'm sure you know this. Like, oh, I should just go over to the toolbox and get the magnet on the little stick, or needle nose pliers. I'm like, no, I can get it. There is a black hole in an F-150 that is like right where this arrow is, and it was like something reached out and grabbed it out of my fingers and pulled it into this little black hole. So then later that day, I had to take the whole center console apart to get to it, because it didn't fall straight down. It fell like a foot away. It like hit something and then moved over. So anyway, this is the story. This is like how this has gone. Like nothing bad has happened. I put it back, put the center console back together, cleaned out all the dirt and dog hair and everything. So
this is life of entrepreneurship right here.
And this was all before I got on the road to the road trip. So anyway, this is the data that I lost 3 times. So this is I got a bunch of different snapshots here. So what you're looking at is the same thing. The load is the red. This is the load, going up and down. I plotted everything on the same plot. I got rid of the units because some of them are actual units, some of them are just digital counts. The gray, these are the individual barometric pressure sensor readings. Now on this one, I didn't have the compensated one, but it's not that big of a deal. It was a cool addition. The purple, or actually I should say the blue, that's the accelerometer. That's the integrated accelerometer velocity. And so because they held it stationary, you can see here that they didn't, when they picked up the load here and they dropped off the load here, there's probably another point down here. They didn't really, they didn't move any. So what happened here, this angle right here, this is just that accelerometer drift of being stationary for a long period of time. Every time you integrate to velocity and then to position, those errors compound. And I haven't corrected that, but on not that one, this guy right here. So this one, when they're actually moving and it was a relatively short time span, you can see that the purple line, the just uncorrected, just straight up integrated position from the accelerometer and the gray position here from the barometric pressure sensor, they track pretty well.
Wow.
And I'm going to get better than that because I haven't corrected any of that. I haven't fused them or really done. I haven't really had time to sit down with this. But what I wanted to show on this one, first of all, so 60 feet, that's California. We got 30-foot rods, and everywhere else they do 25-foot. I Not sure exactly why that is. I should know that being from California. But the fun thing here is this, the blue line is the velocity. So you can see that the velocity was increasing, mostly flat here, but still a little bit increasing. And then, oh, here we go. So we get to near the top, and the guy slows it down, and then the velocity drops all the way down here, and then they're just right about at the top, and then it goes back down to zero. So all of this, these velocity changes here affect the load that's applied because it's dynamic.
Yep.
The wave equation should remove that. So this plot right here, when I have time, it's probably going to be a week from now. I'll probably crawl into a little hole and take all this data and crunch through it. But that should equate to a line that corresponds to friction acting along this length of rods. So this was a 4,000 foot well. This was the sixth stroke. So they pulled out probably, I don't know, what, 6 times 60. Yes, I can't do the math. This is why I don't do math in public. They pulled out, I don't know, let's say 100 or 200 feet of rods at this point. But they still have 38, let's say 3,800 feet of rods in the hole. That should tell me how much friction was acting on that 3,800 feet. When they pull out another section, I should get another one slightly shorter, should get another one slightly shorter. And after they pull past a crook in the well, then that should change. So that's the series of trash cans that I'm trying to get here.
There we go.
That's a lot. Any questions?
No, nothing's come in. I don't have anything. It's starting to get
Too technical?
I wouldn't say too technical, but it's definitely getting into where like I still got to keep listening to more stuff before I can start adding in any worthy questions.
Yeah, so I picked out some random. So here's the 7th stand of rods, and then I skipped ahead to the 42nd. So you can see the load drop off between these two because there's a lot less rods in the hole. So if I compare this one against that last one, there's a load difference, but the amount of friction acting on that should also be different. And it should be different because of the side load that's applied, because there's less tension up high because there's less load on the rods. But it should also be significantly less, because if that rod the bottom rod has passed some deviation in the wellbore, now it's not acting on that. So that's the comparison that I'm so close to getting.
Well, don't stop now. I mean, yeah. I mean, this is definitely some fascinating stuff, and how all of it correlates right back into kind of the torque and drag when we're drilling the wells.
Yeah. So I mean, I just threw these guys in here. So yeah, I guess this is mostly wrapping it up, but there's no torque in this. It's just strict drag analysis. I do actually have this other project that I'm working on. I was going to talk about some torque stuff and a whole nother aspect of it that's going to be cool in itself. But I'm not ready to go blabbing about that. The cool thing about this is you strap that onto the workover rig, and then the rig crew just does what they normally do. So it's basically free data, it's amazing. If I told somebody, hey, I want you to go pull a well because I want to map your friction, that's crazy. But you're already doing the thing that's costing a lot of money. So just throwing that on and gathering the data, it's already there. Just capture it. That was the impetus of that. It's also different because it's from a torque drag analysis, because this is metal on metal, or sometimes we use fiberglass rods, or sometimes there's thermoplastics in the well from like coated tubing or rod guides. So there's different friction. There's different friction properties that are at play in a cased hole, inside tubing, rod on tubing, than there is in an open hole. I don't understand the friction in an open hole. All I've ever dealt with is the metal on metal or fiberglass on metal stuff. Scale. Oh man, I went to Garrison Brothers yesterday, and they had their water pipe that had scale in it. So I had to take a picture of that because I'm sure I'm going to use that. Garrison Brothers, the distillery.
Yeah.
I guess they got a lot of scale in their well water, and so they had a piece of PVC pipe with a pretty thick layer of scale on it. So I'm going to use that in some presentation here in the not too distant future. What else do I need? Friction is complicated. There's all these different contact points, and I didn't even play the one video where I show the echo of an impact going up and down the rod string. I mean, these rod strings are moving in different directions at different times. It's a very complicated system. It's hard to kind of like wrap your head around, let alone all the friction in there. Let's see what else. So what's the point? Yeah. So the workover rigs, it's the most expensive thing you're going to do on a well. And I mean, you actually use workover rigs to abandon wells anyway. But the whole thing about the drilling affecting the life of the well is workovers are the most expensive thing that you're going to do, because you got to get a 4-man crew out there. They got to work for a couple days. If something breaks, then they got to do fishing jobs. It's a very expensive thing. You'd ideally like to minimize that, but geez, I mean, if you're doing something that's very expensive and you're getting practically no data out of it. So this is something that could, I mean, if you could throw it on, you could get a wealth of data. If nothing else, you could see what the rig crew was doing. Right? I mean, they're not going to like it, but like, how fast were you running the rods? Were you dropping the rods too fast? I mean, there's some companies have rules of like speed limits of don't drop the rods too fast because you could damage them. How do you enforce that? Well, something like this could do that. When did the rig crew take lunch? Probably not going to like that, but there's some other pieces like the live view. I mean, a lot of things like when you're trying to find the bottom of the hole, the guy really, it's just up to his judgment. Like, did he feel that? Did he feel it hit bottom? This could tell you, like live, you could see it. There would be no question about were you on bottom. If you're thinking about running a high resolution survey, but you don't have any reason to, you can't justify that to upper management. I mean, this could give you like that one with the missing survey point. The reason they didn't do the Colorado one that had that missing drilling survey point, they didn't want to do that because there was some politics and some corporate politics involved with that one. But if you want to justify, hey, I want to run a high resolution survey because I think something wacky is going on at 5,000 feet, well, this could maybe give you some ammunition at a lower cost to come out and do that high resolution survey. The stats on the workover job, I mean, the rig crews probably won't like somebody looking over their shoulder, but I think that really comes down to how is it managed on the who's paying it side. Yeah, on the management side. Yeah. This could be really good if you're not using it to badger the rig crew to run faster. We want rig crews to go slow and take their time, handle the equipment nice. So, and weird things happen. I mean, the data. I mean, there's some things where I look up and they're yelling, and one of the rods is flopping, and I'm like, well, I'm going to see that in the data later. Yeah, so it's a science project right now, but I did get the patent on it. So if anyone wants to talk about that, that'd be a fun discussion. I don't know if there's any applications in drilling. I mean, the pressure sensor, I mean, knowing where your blocks are relative, maybe knowing something more than the stretch of like when you have the rotary encoder on the drum telling you how much is in the hole. I mean, is that accurate enough, or do you need something more accurate that can run on the blocks and tell you where they are specifically, as opposed to through a stretchy length of cable? I don't know.
Not a question that I can answer.
Yeah, I don't know anything about drilling. While I'm looking at this was actually the very, very first run. This little white speck right here, that was me strapping it into a bag because it had batteries on it. I didn't want them to fall down. That was the first no load, but just the position measurement.
And I think there could be some drilling. I mean, that's a conversation for another time.
Well, and I guess I'll throw it the other way. I mean, there's probably some applications for the torque or the drag analysis models in the production world, but we don't share those. They aren't shared with us very readily. So if somebody has drag analysis software and wants to talk about that, nobody in production really wants to spend any money because we're trying to reduce our cost, because every time a well fails because of something that's crooked in the wellbore, we don't have a lot of funds to spend on fun stuff like this. Oh, and then I'm actually doing a talk on this. I'm writing a paper. I wrote a paper on this for the short course that was scheduled before COVID. So every year they do a Texas Tech. They do the Southwest Petroleum short course. It's a really like technical artificial lift conference. So I wrote the paper before COVID. They canceled it from COVID, and then I ended up not getting data from it. And so this is the follow-up paper where I actually have data and I can actually talk intelligently about what it actually can do. And then there's if you're interested in rod pumping, there's a workshop in Midland. It's from the ALRDC. It's the Artificial Lift Research and Development Council. They put on a bunch of fun little workshops throughout the year. And then there's my contact info. Did I make it under 2 hours? Good deal.
Yeah, made it under 2 hours. Walter, thank you so much, man. I really do appreciate this. This has been like absolutely amazing. I love all the stories and all the information to be able to go along with it. We'll go ahead and take this off here. Yeah, if you guys want to, be sure to screenshot this or be able to get in touch with Walter. No, we don't really have any questions that have come up, but man, this has been absolutely fascinating. I'm guessing there's probably going to be a lot more people that watch this over the weekend. Most people do. And then maybe having some handful of people reaching out to you. I definitely think that there's some great applications to where on the drilling side to be able to look at this and be able to integrate. But it's barbecue time. I can smell it. It's sitting in the other room. Thanks everybody for watching. Do appreciate it, guys. As always, do like, share, subscribe, give us some feedback. Let us know what you think. John DeWar says, great presentation, very interesting and valuable content. Well, that's what I try to do every week. And Walter, thank you for being able to bring it here to everybody. Headed off to Norway tomorrow. For anybody else that's going to the SBE IADC conference in Stavanger next week, I will see you there. If you see me, just come say hi. I'll be the guy wearing the bright orange shoes. Try to think of anything else I get to say. That's about it. We're going to be doing some next week. We're going to be doing some replays, or not next week. It'll be next week and the week after that because I'm traveling. We'll be doing some reruns or replays of some of our prior Vidor Locksmith episodes. So the show will still go on at 10 a.m. next week. We're just going to have some old episodes being played. So be sure to check those out. I think the first one we're going to do is we'll do one of the episodes with Fred Dupriest. We'll do that one, maybe one of the Brandon Foster episodes, just because he's been so popular as of lately. I think that's about it. Thank you guys for watching. Really do appreciate it. Let me go ahead and hit the little thing. Where is it at? There we go. And as always, know your industry.